With every discipline, there exists proven methods that should be used to prevent redundancies when solving common problems. A physicist refers to equations, a medical surgeon relies on common surgical procedures, a chemist uses a chemical equation to describe the symbolic representation of a chemical reaction, and a mathematician or computer scientist utilizes algorithms.
Hello, and welcome back to my channel. In today's episode of
Wow! How'd you code that?
We'll be leveraging a familiar computer science algorithm to solve the HackerRank Challenge Common Child.
In this challenge, the problem statement reads: a string is said to be a child of another string if it can be formed by deleting 0 or more characters from the other string. Given two strings of equal length, what's the longest string that can be constructed such that it is a child of both?
For example, ABCD and ABDC have two children with a maximum length of 3, ABC and ABD. They can be formed by eliminating either the D or C from both strings. Note that we will not consider ABCD as a common child because we can't rearrange characters, and ABCD is not equal to ABDC.
The longest common subsequence is a classic computer science problem, the basis of data comparison programs such as the Unix diff utility, and has applications in computational linguistics and bioinformatics. It is also widely used by revision control systems such as Git, for reconciling multiple changes made to a revision-controlled collection of files. The longest common subsequence should not be confused with the longest common substring problem, which is used to find the longest string, or strings, that is a substring, or are substrings, of two or more strings.
In the following example, the longest string that can be formed between the two strings, while maintaining the order R, N, H, and A, for a length of 3. Rather than reinvent the wheel, let's understand how the longest common subsequence algorithm can be used to solve this problem. First, we define a two-dimensional array, named C, and set the maximum size of each dimension to the length of the incoming strings, plus 1.
The following table represents our two-dimensional array, and will store the longest common subsequence for the given pair of strings. The second column and second row have been filled in with empty values, because when an empty sequence is compared with a non-empty sequence, the longest common subsequence is always an empty sequence.
Next, we define a nested loop, with the outer loop traversing each character in the first string, beginning with the second character. Next, the inner loop will traverse each character in the second string, beginning with the second character. Next, if the character at position I-1 in the first string equals the character at position J-1 in the second string, then the value in the position of I, J in the two-dimensional array, C, is set to the value at the position diagonal to this element, plus 1. Otherwise, the value in the position of I, J in the two-dimensional array, C, is set to the maximum value of the element adjacent to the left of this element, and the element above it. Once all characters have been evaluated, the value at the element at the maximum position in the two-dimensional array is returned to the caller.
So how, and why, does the lowest common subsequence algorithm work?
Good question. The lowest common subsequence algorithm has an optimal substructure, meaning the problem can be broken down into smaller, simpler subproblems, which can in turn be broken down into simpler subproblems, and so on, until, finally, the solution becomes trivial, as depicted in the following recursion tree for the Fibonacci sequence of the number 5. This algorithm, in particular, has overlapping subproblems, meaning the solutions to high-level subproblems often reuse solutions to lower-level subproblems. Problems with these two properties are amenable to dynamic programming approaches, which is both a mathematical optimization method and a computer programming method, and explains why the algorithm works so efficiently.
I hope you found this video helpful. If so, please like, share, and comment below. Thank you for watching.
And we'll see you in the next episode of
Wow! How'd you code that?